As I mentioned in section 6.7, I normally teach these in a different order, but I wanted to stick with what the textbook had. So what they do in this section is they say when we have an electron configuration, it's going to show how the electrons are distributed. And it's N, L, and X. N is going to be our shell or our principal quantum number. L is going to be our subshell. That'll be the letters S, P, D, or F. And X will be the number of electrons in that subshell. It can either be empty, or it could have one electron, or it could have two electrons. So again, it's just a shorthand, and my gut feel is most of you saw this in high school. But just in case you didn't, hydrogen is a 1s1, helium is a 1s2, lithium is a 1s2, 2s1, beryllium is a 1s2, 2s2. There's a table of the entire electron configurations in the next section. I'm going to tell you to refer to it when we get to section 6.9. Now, when I do a configuration, I normally do the ground state, and we are Gen Chem. I can't think of many exceptions that you would have. So that also will make sense in section 6.9. When I do an orbital diagram, oh no, I did that above. The electrons are indicated by an arrow up or an arrow down. So when I have an orbital diagram for an S, I could have an arrow up, and if it is populated, an arrow down. When I have the P's, I will have an arrow up, an arrow up, an arrow up, and then I will do my arrows down. That's going to be coming up as another principle. So again, I used to teach this in just a different way, but I'm going to try to follow your textbook. So Hund's rule, which has been verified by experiment, says if I have degenerate orbitals, and by that I'm going to give an example, the lowest energy is obtained when the number of electrons having the same spin is maximized. Well, those are a lot of words. Let's break that down to show what we mean. For carbon, we have a 1s2. Here's my 1s2. Filling in my three different options, my 2s2, filling in my three different options, and then what's going to happen when I start to fill up the P's? Could I put both of them together? Could I make them paired? Could I give them separate places and have them be opposite spins? Or could I make them unpaired in this manner? Well, as it said, Hund's rule is verified by experiment. This was not verified by experiment. This was not verified by experiment. And what we have is unpaired electrons. We will put electrons in until we fill up the entire set of orbitals, until we start to pair them back up. And when I say experiment, when people looked at carbon, they saw it was paramagnetic, and the magnetism corresponded to two unpaired electrons. So what are these new terms? What's paramagnetic? Paramagnetic indicates you have unpaired electrons. They're attracted by a magnetic field. Diamagnetic, we say all the electrons are paired and they are not attracted. We will use these terms in chapter 9, almost at the end of the course. So again, kind of file them away for later. What else is in this chapter? Well, I didn't know whether to put this or not. You can look at it yourself also, but it lists all the elements in N equals 2. I wish they had put the last one, well, they actually put in the next one. They actually put in sodium. But again, if this is new to you, please spend a little bit of time, because notice how we build things up, how that new electron, where is it that it is going? Well, this is kind of bad. They should have put everything here in the middle, but they did not. So again, take a look at that to satisfy yourself. Now, when we're writing electron configurations for elements that have many, many electrons, it would be very laborious and tedious. So what we do is we have what is called a condensed electron configuration. Because when we're going to be doing chemistry, we only want to know what's happening with those outermost electrons. And so we're going to say whatever is a noble gas configuration, or called a full shell, we will put those things into brackets. Instead of writing everything that would stand for neon, I will instead write neon. And it goes all the way through the periodic table. The thing to notice is the core electrons, they are the inner shell electrons. They are going to be the ones in the brackets, or if we have a transition metal, it's when it's totally full. What we're really going to focus in is the valence electrons, which are the ones in the outer shell. So when I say carbon, what I'm really going to be doing with carbon is saying it has a helium core, and then what it has going for it is a 2s2 2p2. That's the shorthand we have because we know it's the s2p2 electrons that are going to be involved in bonding. Carbon is going to be a special case. It's going to undergo hybridization in chapter 9. So pick this up now and it'll help us later. All right. Transition metals. What are the transition metals doing? Well, they're the ones with the d orbitals, and what you will do is you first fill the 4s. I'll show that in the next section, how you run your finger across the periodic table. And these are the elements, scanadium to zinc, in the third row and the fourth row of the periodic table. Once you fill up all those 3 Ds, then you're going to start to fill up the 4 Ps. There are some anomalous materials, but the textbook puts them in section 6.9. I'll address it there. There's also something called the lanthanide and the actinide, and they have f orbitals. The lanthanide, when you look at the 6th row, you're going to say, well, there's a break. And that's the elements 57 to 70, and they're placed below. They are a very valued commodity. I have one more slide at the end because I knew reading the Wall Street Journal how prices of these things vary, countries fight over who has what. So I thought it would be a good idea to mention that these are used in many places: electric cars, lithium-ion batteries, computer hard drives, solar panels, wind turbines. So again, some reality to this course. The other ones that have f orbitals are the actinides, and they are the 7th row break, and all of them are radioactive. That's where you find things like uranium. So to wrap this up, no, this is not Gen Chem, but this is all the lanthanide elements. And again, Gen Chem, nobody majors in it. Many of you are going to go into many different areas. And if you're going into business, money is very important. But they are used in computing, in clean energy technologies, in defense, in communications, in health. And there is a world demand for these resources. So these are kind of really funky looking graphics, but I thought it's a great way to end this section. Again, I think most of this is review from high school. If it is not, please ask questions so that we can help you learn.